kind of. I mean, it's fine, but since we are here. Okay. Yeah, very good afternoon to all of you present here. So yeah, we have reached the final day of Devcon. We have had like 10 different talks on preconfirmations, 3 full-scale events, and the only question that I've been getting is, how do you make all of this? Like fast transaction confirmations, yeah, we get it, but how do you make this? So yeah, now on the last day, welcome to the workshop on designing an end-to-end system for based preconfirmations. A quick introduction of the speakers. Ahmad, go ahead.
Yeah. So my name is Ahmad Bitar. I work as an Ethereum core developer. Normally, I'm also the product manager of Surge and the technical lead for our preconfirmation solution.
And I'm Anshu. I am working as a blockchain engineer at Nethermind. And I joined this industry like 5 years ago, mostly focused on DeFi. But for the past 6 months, my efforts have been mostly concentrated on based preconfirmations. So today, this session is a no-code session. So I won't be like writing a line of code and then asking you to copy it and repeat it like 100 times over. I know most of you will leave in like half an hour if I do that. So instead, this is a session on design thinking, where we'll build the whole concept from ground up and share what exactly we did during our research over the past 6 months. But if you are interested in looking at the code, then I have linked it below. It's Taiko preconf AVS repository, which you can find on the Nethermind GitHub page. So since we want to build it all up from ground up, we have to start with the foundational knowledge, which is rollups, because the based in based preconfirmations comes from based rollups. So just by show of hands, how many of you do understand what a rollup is? Okay, pretty much everyone. That's great. Well, rollup is a scaling solution. And why do we need a scaling solution? We need a scaling solution because the L1 is really slow. The throughput of L1 is not much. And why exactly is that the case? Well, in a blockchain, blocks are basically a consensus on state transition. That's the first section of the Ethereum white paper. You have state A, you put a bunch of transactions and apply it to state A, which is like a delta, and you get a state B. But now imagine millions of nodes doing this every single epoch. Now that's going to make this network really slow, and that's a major problem. So what's the roll-up way of doing it? Well, if processing state transitions is the biggest issue on the L1, what if we process these state transitions off-chain or apply these deltas off-chain? And that's exactly what a rollup does. We have you can have a one single rollup node or an L2 node, since it becomes a layer 2, that applies this delta off-chain, processes the state transition, and the L1 is just an observer. On the L1, you have a rollup inbox contract, and you simply push the state transition and the delta, maybe as a form of a blob, or in the call data, in the image it's a blob, and the L1 is just an observer. And in the most basic form, this is what a rollup is. But is this enough? Well, no. Because if it's just one node pushing the transition and the delta, how do we know whether it's actually correct or not? And this is where the flavors of the rollups come in, optimistic and ZK. In the case of an optimistic rollup, well, you push the state transition and the delta, and then you just wait. You just wait for someone to prove you incorrect. If you're correct, it's all good. But someone can just come by and say, oh, hey, it's a proof. Here's a proof. This transition that you posted is not possible with the delta that you posted. And then you kind of get slashed if you have some stake in. Depends on what kind of process the rollup wants to do. And Arbitrum is an example of an optimistic rollup. I guess most of you must have used Arbitrum. And then we have ZK rollups. In the case of ZK rollups, instead of waiting on for someone to prove you incorrect, the moment you push the transition and the delta, you have to prove that this is correct. So it's called a validity proof. You're basically proving the validity of the transition. But the point here is that whatever time or computational effort it takes to verify this validity proof must be less than what it takes for the L1 itself to process all the data. Only then it actually makes sense, right? So these are the two variants for proving whether a transition is correct or not. Once again, by show of hands, how many of you have heard of centralized sequencing? Okay. It's the most cursed concept right now. And just to give a quick primer, when you're making a transaction on Arbitrum, you're not directly sending the transaction to a public mempool, like when you are transacting on Ethereum L1. Instead, it's going to an Arbitrum sequencer. And it's a private server. What the sequencer does is it has complete control over arranging or ordering the transactions. And they usually promise that they will arrange the transaction in a certain way. We don't know whether they're actually doing it or not. But in the case of Arbitrum, the promise is that it's a first come, first serve. If your transaction comes before that other person, we'll put your transaction first in the block. But once again, it's a promise. We don't know whether that's actually happening or not. So let's get based and talk about based rollups and preconfirmations. Well, the based part is actually not a different variant of a rollup, so it doesn't stand beside our optimistic or ZK rollup. Instead, based is a form of sequencing. Just like we have centralized sequencing, we have base sequencing. And in the case of base sequencing, the L1 proposer is the sequencer. You don't have a centralized server sequencing the transactions. Instead, it's the L1 proposer. Let's say we have Taiko. Taiko is a based rollup. And in the case of Taiko, the L1 proposer literally runs a Taiko software alongside the usual consensus and execution clients. And whenever their block comes in, they literally just pull the L2 transactions from a public Taiko mempool, they order it in their L1 block and put it on the network. So yeah, you basically are inheriting the L1 security as well as the L1 liveness, because the L1 itself is your sequencer. So just a quick overview of how Taiko actually is arranged. Well, you have the Rollups inbox contract that I have been talking about. And although Taiko doesn't really call it rollup inbox, this is the colloquial term. Taiko has like a bunch of contracts that work together, and they just call it Taiko L1 contract. So that's the L1 component. Now, if you're running an Ethereum validator, you usually run an execution client and a consensus client, right? So in a similar way, if you want to run or be a part of an L2 network, the proposer has to run an L2 execution client or an L2 consensus client. So in this case, Taiko get is the execution client, which is a modification of the standard Go Ethereum. And this is where you have the mempool, you have the actual L2 chain, all the blocks are formalized, and you also have the EVM on the L2 network. And then we have the Taiko client, which has some subcomponents. And this forms the consensus client, and it deals with proving the blocks and proposing the blocks whenever required. Now today, the most important thing for us are block proposals, because that's where the whole concept of preconfirmations will be built upon. So how exactly block proposals work in Taiko or in a based rollup? So well, when you're making a transaction using any kind of standard wallet, it goes to the mempool, or the public mempool, which is offered by Taiko Get. And every few seconds, or depending upon what algorithm the proposer is using, transactions are fetched from the mempool. And this transaction batch forms the actual delta. And when you're calling the rollup inbox contract, you're basically calling a function, which is proposed block, and you're just passing this delta along. Now, you might be wondering, well, that's the delta, fine. Where's the transition? So in Taiko, it's a two-step process. The delta is gone, and now we have the Taiko prover, which comes in later on and just says, OK, remember that delta that was pushed a few seconds ago or a few minutes ago? You see, this is the transition that that delta causes. And since Taiko is a ZK rollup, it pushes a concise proof along with it, like, OK, this is the transition, and this is the proof that the delta caused this transition. Now the most important aspect, Taiko driver. So once these L2 blocks are put on L1, there is a block proposed event that is released, which shows that, hey, OK, this L2 block was put in the L1 contract. And whenever that block proposed event is released, Taiko driver listens to it and advances the head in get. Advancing the head basically means you're formalizing and putting an L2 block within the L2 network. And this is when the wallets end up getting the transaction receipt or the confirmation. So you see, the catch here is that Taiko driver only receives the block proposed event every 12 seconds. That means when you're making a transaction on Taiko, you get a transaction receipt after 12 seconds, which is huge. That's not ideal for a rollup or a scaling solution. And that's very evident from the Dune analytics graph of Taiko's block times. It's average between 12 to 24 seconds, which makes sense. It's inheriting L1 block time. That's not ideal at all. So we need preconfirmations. And preconfirmations is not something new. We have already had it on Arbitrum for a long while and several other rollups. Again, show of hands, how many of you have transacted on Arbitrum? And when you transact on Arbitrum, you basically get a transaction receipt like in a very small period of time, like half a second, 1 second, sometimes 2 seconds. But the point here is that Arbitrum only posts blocks every 2 minutes on L1. So how are you getting this transaction receipt immediately? It's because that's a pre-confirmation. They're giving you a promise that, hey, see, this is the receipt, and we will be putting this on the L1 eventually. In Taiko, you have to wait for it to be put on the L1. But well, this gives better UX for Arbitrum and bad UX to Taiko. Now, what if we want to put preconfirmations on Taiko? It's really tricky, because in the case of Arbitrum, we have one server, literally one server in one corner of the world, just running, except ordering transactions, providing preconfirmations, easy. In the case of based rollups, the sequencer is changing every single slot. The proposer changes every single slot. So, well, the sequencer changes every single slot. And then, these days, we don't have the proposer building the blocks. The blocks are actually built via a PBS pipeline, like MEV Boost by Flashbots, where builders build the blocks for you, or for you as the proposer, and then you just propose the block, whichever builder gives you the highest bid, you just take their block and propose it. You don't even have any control over what's in the block. So how exactly will you put in base preconfirmations with 3 layers of complexity? Well, we have done it, and let's start with the design principles. Maybe a quick round of questions if anyone has any questions. No? OK. Take it over.
All right. Great. Thank you. OK. So the first thing we wanted to do was we wanted to not introduce centralization again. And the way we wanted to, the idea here is that if we wanted to introduce centralization, we wouldn't have built it as a based rollup in the first place. Then how are we going to solve this complex problem? So let me explain how gateways work first. So gateways are basically centralized servers that expose an RPC for the user to be able to provide them the preconf. The user sends the transaction to the RPC, and then it selects which transactions it wants to preconf, and then it provides it to, it proposes that block to L1. Of course, the confirmation receipt that goes to the user is given like in a matter of milliseconds, between 100 and 200 milliseconds, which is very fast. Of course, the UX is very cool, but the compromise is very high. Now, also, like, there is another concept here in preconfirmation that is important, which is not all validator has signed up to become preconfers. And because of this, you sometimes have some validators who have decided to register as a preconfer and some others that haven't registered. So the gateway can provide preconfirmation for users, and it not necessarily will push a block, propose a block for the L2 on this slot, but it could potentially push it here. And the way to do this will be explained in a later stage when we talk about forced inclusion lists. All right. The other thing that we wanted to focus on, which was important for us, is that we wanted to use the existing transaction structure, the existing wallets. We didn't want to invent a new like complexity to the already existing situation when you are sending transactions through wallets. So some suggestions in the preconfig space were like, oh, we should potentially put an inclusion preconf fee premium. So like, what are you going to pay the preconfer so he can provide you with this fast service? And the base fee per gas for that as well. Or, for example, an execution preconf, yeah, it's basically very similar to each other. Like, they're all like the same. So what we decided is, no, we're going to choose something that is basic. So we're going to choose the same exact EIP 1559 fields, which is the priority fee. So the priority fee pays for the preconfirmation, the proposing, and the proving of that transaction. And the user does not have to worry about all of these complex things, other things. OK. It's not moving. OK. All right, so I'll start now explaining what we designed. So in Taiko, like explained, we have the Taiko client, and we also have Taiko get. In Taiko also we have, before we come to these, we have the contract that receives the block proposals. And so what we did is we added something we call a preconfig node. And that sits between the proposer and the contracts. And we added some contracts. One contract is the preconfirmation service contract that basically receives the blocks that are coming from the preconfer. And also, we added a re or staking contract that will basically allow the proposers to register as a preconfer. And by this, these proposers, whichever they are, any validator, can basically just run this set of software as a sidecar to whatever they're running for the validator. So alongside L1, you're just running these three, Docker images, Docker containers, and then you are able to preconf transactions when your slot is up. So how does this exactly work? So we have a loop that happens every 3 seconds. When you are chosen as the preconfer for the upcoming slot, what happens is that you, as a preconfig node, will fetch the transactions every 3 seconds from the Taiko proposer, which will basically fetch them from Taiko get. The user will have sent this transaction to the mempool, so there is no centralizing aspect here. You don't have to connect to a specific endpoint to send the transaction. And every 3 seconds, the preconfer will sign this batch of transactions that it has received from the Taiko proposer, and then broadcast it to other preconfers through P2P. Oops. OK. OK, permissionless. OK, so here we look at, OK, so how do we choose which of the registered preconfers are going to be used or have the right to propose these blocks? And this is when we use the lookahead that is provided by the consensus layer to know which exactly is the proposer that has been registered in the upcoming 64 or like in this epoch and in the epoch after. So in consensus layer and beacon chain, you can query the CL client for the existing epoch, the current epoch, which validators have the right to propose, and for the upcoming epoch. So it provides you with a list, 32 long list of after you specify the epoch that you want. And so basically what we did is that we made the preconf node fetch this list from the CL client and push it to the preconfirmation service. And this way, we know, for example, that since this proposer is not registered, this proposer is not registered, we know that this proposer is registered, so then we choose this proposer to be the one who is preconfing those blocks. This thing doesn't always work. It's just, OK. So then there is like, with any system, you have to have incentive to act correctly. Some systems depend on only rewarding good behavior. Some systems depend on punishing bad behavior. Most systems, or a lot of systems, depend on doing both. So in this case, the preconfer gets the preconfirmation fees and the proposing fees. In return, he needs to preconf and provide good information and honor the preconfirmations that he gave to the users. The way we check that is that in the case, the preconfer node reveals the signed malicious preconfirmation. The way it's done is that, so let's say I preconfed a batch of transaction, and then I didn't end up pushing this batch of transactions on chain. But I have already broadcasted that I have preconfed this batch of transaction with my signature. So what would happen is another preconfer that was listening on P2P would then pick this signature with the batch of transactions and push that to the preconfirmation service contract. The preconfirmation service contract would check if this is a valid signature for the preconfer of this slot, and if it is, then it will go and ask the restaking or staking contract to slash the signer. And in this case, there is also the slashing for the incorrect lookahead, because you fish the lookahead from the CL, but how does the EL know that this lookahead is correct? You can use 4788 EIP, which basically provides you with the CL beacon root. And using that, you can push a proof if the lookahead is incorrect, and the preconfer who sent an incorrect lookahead would be slashed. OK. So before I move on, if you guys have any questions, it's good to have them now. So yeah, please go ahead.
I have two questions. First one is based on, I'm not familiar with 4788, but could you not also prove that, like, can it only prove that the lookahead is false?
Yeah, so the thing about 4788 is that it provides you with the beacon root of the parent block and not the current block. And because of this, when the lookahead is pushed, I cannot, in that moment, verify its correctness. But after one single block, I can, with the proof, using 4788, make sure that if it's not correct, that it is not. So this is why we opted for this. In the case that it was possible to verify, we would have potentially opted for pushing the proof with the lookahead. The problem with that normally entails that you would pay more because the proof needs to be verified on chain in every single submission. Whereas if you do it in a fraud-proof manner, only when someone is acting maliciously that you need to do this. So the cost drops dramatically. And there is precautions to this. So whoever is submitting the lookahead will get rewarded. Submitting the proof, the fraud proof for the lookahead will get rewarded for this by the slashing of the other preconfer. Other questions? Yeah.
Yeah. Could you get back to the slide where those slots where that was someone to do with the preconfs and one wasn't?
OK. Let me try to make this work somehow. OK. Work, please. OK, no. OK. Yeah, over here. Sure.
Well, not this wondering.
I mean, here, this one is not opted in, and this one is.
So, for example, if I take preconfirmations from someone who's 2 slots ahead, right?
Yeah.
How can they provide reliable stake commitments where the stake could possibly affect that commitment in the previous proposals?
Okay. So this is probably not mentioned in this presentation, which is a problem, but hey, sorry. Basically, based rollups depend on giving the user the ability to always push transactions on the L1 with permissionlessly. Okay, and that means that there is no one who could prevent the user from pushing a transaction that could invalidate future transactions that have been preconfed, that will be pushed later, that have been preconfed. And this leads to execution preconfs not being able to be provided. And the only solution that we have to that is delayed inbox. So preconfers are able to push directly to the Taiko smart contract to propose blocks, whereas normal users who don't want to use the preconfing system that is built and want to push directly to avoid potentially censorship by the preconfer, even though this is a decentralized solution, it could potentially have some type of censorship. So if they push their transaction to this delayed inbox, what happens is that we wait for the preconfirmations to land, and then we include those transactions that have been pushed by the user. So in this instance, just to be clear, any transactions that come in this slot will go to the queue and will not be proposed. No, it will not be denied. It will go to the queue. Yeah, delayed, yes. It will be delayed till after the preconfer has pushed his preconfirmations, and then it will be included.
What if my preconfirmation is dependent on L1 state, which is like a really nice component of based rollups?
Yeah, no.
I could affect the preconfirmation with interacting with L1 as opposed to...
Yes, so if we engage composability in here, then it could, yes, any L1 state change could potentially affect this L2 transaction that depends on it. And this is not a problem that the solution is trying to solve, unfortunately.
So it's like an edge case?
Yeah, I don't think like, as of now, there is, potentially there's some people working on this, but I'm not aware of any solution to this particular problem. This is a very good question. Thank you, sir. Any other questions? Yeah, go ahead.
Does this require that at least one preconfer is however in the next lookahead?
Yeah, so I think this might be talked about in a later stage, so I'm not going to touch on it more. But there is a way for choosing a random preconfer in the case that there isn't a preconfer available for the next 64 block slots. Any other questions? Yeah, go ahead.
Could you touch on more about so I'm viewing the preconf gateway as like a subset of the P2P layer that's exclusive for preconfers and that's uninteractive. This immediately sounds like a loosely coupled system to me off the bat. Do you feel like there's consensus required here to agree on preconfirmation state? Like what happens if the proposer needs to fall back to another? Like could you unpack the gateway for me?
The gateway. Okay. So the gateway basically buys the right from the proposers that have registered at preconfers to propose at a certain slot.
Do they need to agree on like for example, the tip the user's providing? Like
I don't think so. No, like they can have varying tips between one gateway to another. The problem is that with gateways is that the gateways will have to compete in the beginning. We might have a couple of gateways out there. The problem with that is that people normally end up converging into a couple of gateways that then would have a monopoly. So like 2 or 1 gateway that would then be dominating. Because the idea here is that if a gateway cannot secure validators or proposers that are willing to sell the gateway their right to propose these Taiko transactions, the gateway cannot operate.
Would there ever be an instance where preconfirmation
Yeah. So
Any consensus there?
you do, and that's why we have the P2P. I'll explain that in this slide. So when we said here, sorry, this thing is not that. Okay, yeah, so when we said that the preconf node every 3 seconds batches a transaction, takes a batch of transaction and signs it, and then it broadcasts the signed preconf blocks on P2P. This is important because anyone who's listening can do a bunch of things. First, they can advance the head of the Taiko
right?
geth,
Yeah.
so people can keep up with these preconfirmation
Are you moving
blocks.
to a safe head there?
Sorry?
Is it moving just to a safe head?
It's not a safe head, no. It's not even a safe head at this point because
Okay.
it's basically a soft head, very
Yeah,
soft head.
so
Because
unsafe.
as long as it hasn't been proposed on L1, it's not fully safe. I mean, there is financial precautions to the preconfer if he doesn't obey or honor these preconfirmations, but software can always fail, or they could potentially have other incentives. So it's a very soft head, but at least you get consistent block times, which is a better user experience than what you get right now. I mean, Anshu said that transactions normally take 12 seconds, and on Taiko, sometimes they take 20 seconds. So there is some kind of extra delay. It's very long time. Any other questions before moving on?
Sorry, I just wanted to understand the consensus at the P2P layer that you were describing.
So what do you mean, the consensus?
So my original question was, if you have preconfirmations being built upon new preconfirmations being built upon the state of previous preconfirmations, how does that like consensus is needed there between
Right.
two different
So
proposals?
the preconfer that comes, so let's say that, okay, let's say that all of these are preconfers. And this one is a preconfer and has been pushing, it pushed basically 4 blocks. It preconfed first one, second one, third one, fourth one, and then it basically just went and pushed it to L1. This one would be listening to these preconfirmation batches on the P2P and would receive them. And it would just wait for a confirmation that they have landed on L1, and then it would start building on top of that.
Would the middle one be accepting preconfirmations before it's been posted to L1?
No, because since it's preconfirmation, depends on the state of what happens in the chain here, so it can't do that. Or it will collect, I mean, it can, but it will collect a bunch of potentially a bunch of transactions that has been already included, for example. So it would potentially lose that space on the L1 side. And yeah, and also if it does not, if it, for example, preconfs a bunch of transactions that then already has landed, the execution preconf is not honored, that doesn't mean that it will be slashed. It won't be slashed in the system because the inclusion preconf is still there, but it will lose that. And if it does not include them, it will be slashed. So in both cases, it's kind of losing something. Of course, non-inclusion makes it lose more. So it would include them even though they're already processed and will be invalid if they're included again, but it won't, at least it won't be slashed. Yeah, so this is the consensus. I mean, this is a problem with also like varying types of preconfs because you can always, so in the system right now we're trying to build with preconfirmations is that we're trying to avoid a singular solution to dominate. So there is multiple solutions. So there is the gateway, there is what we're building, and there is multiple ones. So if each one kind of like needs to build on the other one, it needs to wait for the L1, the state of L1 to be updated to start building on top of it. Additionally to that, if a user pushes a transaction directly to L1 without pushing it through a preconfer, then that also changes the state. So it doesn't make any sense at all to start building preconfirmations before knowing the exact state on the L1. Yeah.
Thank you.
Okay. Let's hope this marker starts working. Okay. Yeah, so we talked about slashing. Now, so as we said, the preconfer needs to include and propose these batches of transactions on the L1. But if this validator is selling his right to build the block to through PBS to a builder, it cannot accomplish that because it has no control over the content of that block. And the solution we found to that is that we would modify the ePBS pipeline to accomplish this exact goal. So the preconf node would go and tell basically the MEV boost that there is a constraint on the builder and that the builder needs to include a bunch of L2 blocks, which are basically a couple of L1 transactions, or it could be one L1 transaction and their blobs. And it should include them, and that's why and then the PBS relayer would return with, okay, yeah, I can honor that, and they build a block including these transactions at the end, and we propose the L1 block. This is the way that, and currently we're using Bolt's MEV boost because they have that constraint API already implemented, so we didn't want to re-implement the wheel. But of course, there is also commit boost, which can have that Bolt MEV boost module built on it, and you can have it. For more details on those, please search them on Google, commit boost and Bolt MEV boost. Both of them they have open source GitHub repositories that you can look at, and yeah. Preconfer selection, I think Anshu will take over here. Thank you, sir.
Thank you.
You want the mic?
Yeah, just this one, yeah. Okay, so now you have a good idea of what the overall design looks like. And let's talk about preconfer selection, because we did speak about how we want the L1 proposer to be the only one who can preconf and then propose the L2 blocks in a particular slot. Now, this is actually a very hard problem, even though it doesn't look like, because at Ethereum, we love patching things up, and in the process of patching things up, we develop new problems. So when ETH moved from POW to POS, what happened was we introduced a new layer, the consensus layer, besides the existing execution layer. So earlier it was merged into like one single thing, and now we have it separate. We have a consensus layer, which manages the POS part, and we have the execution layer, which is what we developers usually handle when we are deploying smart contracts or interacting with Ethereum using a wallet. The problem is the consensus layer is where the proposer's identity lives. And that has a BLS signature scheme. But the execution layer, where all the inbox contracts are, where all the transactions are made, that has an ECDSA signature scheme. And that's a big problem. How do we make a connection between both of these? There's no way to make a connection. So what we need is we need a BLS to ECDSA mapping. So let's say I'm an entity, I have an ECDSA address, and I run 1,000 validators with 1,000 different BLS public keys. I need a way that I can prove that I own those 1,000 validators. I can show it to the registry contract. So we have the preconfirmation service contracts actually have 3 subcontracts, the preconfirmation registry, which we'll be dealing with in this slide, and 2 other contracts that we'll be taking up later on. So this entity needs to prove that, hey, I own these validators, and I actually have the right to propose an L2 block in a particular slot. And how exactly do you prove ownership of a key? Through signatures, right? So we have this signature format here, which you can see. It basically has the standard thing like having a chain ID, and then validator op is basically either 0 or 1. If it's 0, you're removing a validator from your list. 1, you're adding. And then there is an expiry and the actual preconfer. So in here, the preconfer in the signature message is the ECDSA address that I'm claiming, that is claiming the ownership of a BLS address. So the ECDSA address just pushes a signature And the contract just verifies that, yeah, the signature is correct, and this BLS public key actually belongs to this ECDSA key, and inserts it into a simple map. Now, the execution layer has no native way of verifying BLS signatures right now, but very soon in the next upgrade, the Pectra upgrade, a new precompile is being added via EIP 2537. That's where all the discussion has happened. And this precompile, or a set of precompiles, 3 precompiles actually, will help us verify BLS signatures. Now, this is really expensive because for verifying one signature, we need to spend like 300K units of gas. That's really expensive. So in our next POC, we are actually proposing an alternative where, in the case of BLS, there's a great feature, and that's aggregation. So if you have 1,000 validators, what you can do is you can have 1,000 signatures off-chain, then add all of these signatures up. It's basically elliptic curve addition. You add these signatures up, and then on the contract, you just have to verify one signature. So essentially, you can add, you can put thousands of validators in your registry via just one signature, and just a bit more than 300K gas, which is amazing. And this is what we will potentially be putting in the next version. But yeah, right now it's one-to-one, single address, single signature every single time. So how is this used to construct the lookahead? Because the BLS lookahead is absolutely useless on that's on the consensus layer. We need an ECDSA lookahead on the execution layer. So every single time we know that only this ECDSA is supposed to propose. No other ECDSA can propose an L2 block. So in this case, it's kind of simple. The preconf node has the logic. The preconf node can take a look at the consensus layer because the preconf node has the view of both the execution layer and the consensus layer. So the preconf node pulls all the proposers from the consensus layer for the next epoch. Then it fetches the associated ECDSA key from the preconfirmation registry because we have the BLS to ECDSA mapping there. And it just matches it. OK, this BLS for the next slot belongs to this ECDSA. This one belongs to this. And it creates the entire lookahead. Now, in our design, we have assigned the duty to push the lookahead, of pushing the lookahead, to the first preconfer of every epoch. So the first preconfer of current epoch will be pushing the lookahead for the next epoch. And they are basically bounded by this duty. They must do it. If they, well, there's no option of not doing it because the contract expects you to provide that. And this is what a simple lookahead, like one of the nodes in the lookahead array or mapping looks like. I'll get to what the lookahead, what data structure we actually use. But in here, the timestamp, the second field and the fourth field makes sense. The timestamp is the timestamp of the slot, and the preconfer is whoever is supposed to be preconfing in that slot or proposing an L2 block. We have another field, fallback, and previous timestamp. Now, what are these? Well, the previous timestamp is just a link to the last lookahead node's timestamp. What this allows us to do is arrange the lookahead as a linked list within the contract, or sort of a linked list. So every lookahead structure is an item in a map, and the previous timestamp just points to one of the other timestamps. What this allows us to do is have advanced proposals, because not every proposer will be opting in, and also not every proposer will be registering and exposing an ECDSA address. Some are just not interested in preconfig, right? So in this case, we cannot just have an entire epoch be empty if there are no preconfers, or if there are very few preconfers. We need to do something in the empty slots. And what we do is we allow the next chosen preconfer to preconf in advance. And because of this link, we can do that with a simple check, a simple if condition. That's why in here you can see that P2, preconfer 2, can preconf in the second and third slot already. And P3 can preconf in 3 slots in advance. That is made possible because of this linked list design. Finally, if we have an epoch where there are no preconfers at all, and that's very much possible if none of the proposers in that epoch has opted in, we don't have anyone as a preconfer, then we have to select someone randomly. And that's a very simple selection. Like, we need a source of randomness, and with apply like simple modulus to select one of the indices of who is exactly going to be the preconfer from the registry. And the source of randomness comes from the beacon root contract. So we, as far as I remember, we basically end up choosing the beacon root of the first block in the last epoch, because this gives us a deterministic idea of who's going to be the random preconfer in the next epoch. So we use that as a source of randomness, and we just use that to pick out a preconfer. And this fallback preconfer has an advantage, and that is it can preconf in every single slot of this epoch, because no one else is there to preconf. Yeah?
Sorry, if preconfer is not in this epoch, doesn't that mean they're highly unlikely to be proposing the blocks? Like if you're not proposing in this epoch, if you're not known to be proposing in this epoch, you might be proposing in 6 months.
In 6 months? Well, but we won't be stopping the system for 6 months, right?
Yeah. So if I can get in here. I understand the question. So you're asking is, since the preconfer does not have the right to propose a block in the next epoch, for example, and we chose it at random, how will it be able to honor these preconfirmations? And the answer to this question is that it might not be able to honor the preconfirmations. But it will not be slashed if it does not honor them in this case, because it's a random picked preconfer. And also, we thought about this like, okay, maybe it shouldn't be providing preconfirmation, but this would be a very bad UX. So we'd provide the preconfirmation, we would send them in the P2P on the mempool, and potentially someone will pick them up and include them if the fee is right. And this was like the mechanism that we wanted to do in the beginning. So what Taiko is doing also is that they're using this fallback mechanism to say, okay, if there is a no preconfer registered in the next epoch, then we are going to propose just to keep the liveness of the chain. And of course, this proposal will go to the mempool and someone will pick it up. But if someone intentionally is censoring these transactions and there is no mechanism to force the builders to include them, then they will potentially not be embedded in time. Yeah.
Thank you, Ahmad. And one thing to note is that throughout this POC, we have never touched the Taiko contracts, although eventually we might to add that delayed inbox. But in here, we have tried to not mess around with the Taiko contract, and what our task manager does is it simply routes the blocks that are being proposed over to Taiko contract. So because of this, the prover architecture doesn't have to change. That's the best part. Nothing in the prover has to change, and the proposer also needs very minor modifications because the original contracts of Taiko have barely been changed. Go ahead for the next step.
Thank you. Thank you. Okay, so now we're going to go back to the preconfirmation loop that we discussed, that every 3 seconds we go and in a bit more details. I hope this clicker works. Okay, I'll just stand here. All right. So first, we start with the normal event loop for Taiko. So what Taiko does is that once every L1 slot, it pulls the pending transactions from the mempool. Taiko proposer goes and forms the block and then pushes it through the blob to the rollup inbox contract through the proposed block function. Very simple, straightforward. What we have with the preconfing solution is the following. So we have the preconf node every 3 seconds requesting from the Taiko proposal a batch of transaction. Taiko proposer goes and fetches those batch of transactions from Taiko get and forms a batch, gives that batch to the preconf node, and The preconf node then goes and then pushes this transaction to the P2P, like we said, the batch of transactions to the P2P. And of course, this also only happens after it made sure that it is the preconfer for this specific, for this slot and or an upcoming slot that is very near. So this is the new loop. Okay, all right. So what do we sign when we provide the preconfirmations through P2P? What's the signature? So the structure that we use is we use the block ID because we need to commit to a specific block height, or that preconfer could potentially sandwich transaction if it wanted to, if we don't commit to a specific block height that it needs to propose this batch at. Also the chain ID, in case we have like multiple chains, and transaction list hash, which is basically just a hash of the RLP encoded transaction list. And I see there are some hands for questions. Yeah, go ahead. You have the mic? It's fine, just raise your voice.
3 seconds.
Yeah, so 3 seconds was like just a conservative random number that we chose at this point because we weren't sure how fast the system would be, the latencies, all of that. What we're going to be working on later, as we will see in one of the slides, is like getting that number lower and seeing how it's going to behave and how it will work. We will talk about that in later slides. Okay. So this works here. Okay. Yeah. So the preconfirmation structure, we saw it, and then there is the preconfirmation object that is sent on P2P, because the preconfirmation structure is the one that can be pushed as a proof for fraud proof. But here, we need to, when we are pushing the preconf batch on P2P, we need more details. That one is not enough. So we have the block height and the pending transaction list, the whole list, and the pending transaction bytes. I'm not entirely sure what that is for, and the proof of the preconf message. And this is what ends up being sent exactly in the P2P. And the reason we need the batch of transactions is because we need all the other preconfers or all of the other participants in the network to be able to advance the head with this batch of transaction. And we also need them to be aware of this, so when their role of preconfing comes along, they know that, okay, these transactions have been already preconfed and potentially will be proposed in the next L1, in the previous L1 block before we start preconfing ourselves. Yeah. So when a preconf node receives the batch of transaction from the P2P, once it has been preconfed, currently the way it works in Taiko before the preconf is that we get an event, which is called block proposed, from the L1, and that goes, the Taiko driver is basically subscribed to this specific event and advances the head once it receives this event, which means that the user will get a transaction receipt every 12 to 24 seconds. And this is the main point that preconfirmations, our preconfirming solution is trying to alleviate with this design. So now the preconfirming node can, once it receives the preconf message with the pending transaction list, it can provide it to Taiko driver, and Taiko driver can basically advance the head of Taiko get in around 3 seconds, given that we choose a 3-second confirmation loop time. All right. So so there is the preconfing node. So this is, the previous slide was about the preconfing node. So once it preconfs the transaction list, it does this. And there is also the non-preconfig node receiving this message through P2P and then sending it to Taiko driver to advance the head. So the whole network advances together and not a single one of the nodes in the network. Yep. So we already kind of discussed this. So we have two ways that the preconfer sends his transactions, or the L1 transactions that will basically push the L2 transaction batches. So first, we said, OK, let's say that we have a preconfer in slot number 5. And this preconfer is on duty for slot number 1, 2, 3, 4, and 5. That means that they need to preconf a lot of batches in these slots, and then they can force include them in slot number 5. And that's not a problem. That's easy to do by using the PBS software like we explained. The problem arises if there are sparse preconfers. There isn't a lot of preconfers. And that would mean that potentially one preconfer could be in slot number 42. And he's responsible for slot, I don't know, 5 up until 42. And this would mean that he needs to push a lot of transactions in his slot if we follow this model. So instead we said, OK, maybe we should just push all the preconf transactions right away to the mempool. So we get batch A, batch B, and we just push them directly to the mempool. And at the same time, we put them in a queue, in a cache. And the idea of this cache is that once an L1 block comes and it has those batch transactions that has been pushed here in it, then we can remove this batch from the cache. If that doesn't happen, then that batch of L2 transactions stays in the cache. And then once it is, yeah, and so basically if it's included, we clear that batch from the cache. Okay, so on the proposal slot, we take the ones that hasn't been included, that we push to the mempool and hasn't been included yet, and we make sure that we push them through the constraints API of Bolt-Smith Boost to be force included by the builder. And then once we receive the L1 block, we have the guarantee from the relayer that these transactions, L1 transactions that contain the L2 transaction batches, are included then in the proposed L1 block. Anshu will talk about slashing and, yeah.
Sorry, you got that? Oh, yeah. OK. So now comes the Preconfirmation Service Manager contract, which we haven't spoken about yet. And this is a very interesting contract because what we have tried to achieve with this POC is a really flexible interfacing. Because we have a number of restaking solutions right now out there in the market. We have Eigenlayer, we have Karak. We might also have our own staking contract later on if a community decides on one, which is actually going on. A discussion is going on having a unified registry. And that calls for having some kind of a middleware contract so that later on the core logic doesn't have to be changed. And the staking is just abstracted away to a different set of contracts. And that's what we achieve with the service manager. It's essentially like a middleware that ensures that only those proposers who have a required stake are allowed to pre-conf or propose in the upcoming blocks, in the upcoming slots. So what kind of slashings do we have, or when exactly do we slash? Well, one time that we do slash is when the lookahead being posted is incorrect, or the lookahead posted is incorrect. A basic version of this is that when you have, like let's say for a validator with BLS public key B5, in the lookahead mapping, in the BLS mapping, you have E4 as the associated individual who owns the B5 key. But the proposer who pushed the lookahead placed E2 as the associated ECDSA key, which is factually incorrect. Now, this might look like an easy way to just compare, hey, okay, both of these are not really equal, so why not we slash the person who posted the lookahead? But it's kind of tricky to prove this inequality because we have B5 and E4 from the preconfirmation registry, but in the task manager, we don't have access to who exactly was the BLS, the validator and its associated BLS key for the current slot or any slot that is incorrect. We don't have that information in a simple way. And what we need to do is we basically need to have this kind of a match that, okay, B5 from the preconfirmation registry and B5 in the current slot, both of them have different ECDSA keys. And then based on the basis of that, we slash the poster of the lookahead. So, well, there is a way to do that, and I kind of have to make a correction on my previous statement that there is no connection between the consensus layer and execution layer. Well, there is, but it's kind of a complicated connection. And that's through the beacon block route, which I think Ahmad touched upon briefly. So you see, just like the consensus layer has blocks, the execution layer has blocks that we deal with, the consensus layer also has beacon blocks because it's the beacon chain. And each beacon block has a state root. And if you unravel like the entire state tree, then you'll realize that in beacon state, we have the validators field, which contains all the validators or the proposers. And that includes their unique index as well as their BLS key. So what EIP 4788 proposes is that we get this eventual Merkle root, like if we Merkleize this entire beacon state and then eventually the beacon block, we eventually get a 132-byte long Merkle root. And we make this available within the execution layer. So the thing here is that there's a problem, and that's we only have access to historical roots. We don't have access to the current slot's proposer because, well, the consensus layer is yet to create the block, so we can't really know who the proposer is. So we have to slash or prove that a lookahead is incorrect optimistically. And the way we do it is we wait until the incorrect slot has passed, and we have the root. And once we have the root, we can basically make a static call to this contract, which is the beacon roots contract, and get that beacon root. And then just need to send two proofs. So first, the challenger posts the BLS key of whoever was supposed to be the validator of that slot, as well as their validator index. And along with this, it sends two proofs. First is the proof that, in this case, if you see, we have a proposer index in the beacon block, but in the beacon state, well, we basically end up having BLS keys of the validators at respective indices. So via a Merkle proof, we have to make this connection that, hey, this proposer index actually belongs to this particular BLS key or BLS public key, and that's the step 2. And then in the next step, the validator, or once again, not the validator, the challenger, needs to prove that this is the proposer index that is present in the beacon block, as you can see here, the second field. So very simply, with two simple Merkle proofs, you are able to get whoever was the BLS key of whoever was the validator in the current slot, or the slot that is being challenged. And well, once you get that, you can just go ahead and check if this inequality is actually satisfied. If it is, then well, the lookahead slot is incorrect, and you can slash whoever posted it. Along with that, we have slashing of bad preconfirmations, which I think was touched upon by Ahmad. But in this case, if we want to expand it, we have execution preconfs that could be bad, and we could also have bad inclusion preconfs. In the case of execution preconfs, well, the proposer did push the eventual block that he preconfirmed, but he misordered the transactions, or maybe inserted a new transaction that was not actually preconfirmed. And in this case, what we end up having is that the transaction list hash is mismatched between the proposed block and the preconfirmed block that was on the P2P. And in the case of inclusion preconfs, that's a bit more simpler, we end up getting different proposers for the same block ID, because it might have happened that, well, he pre-confirmed, but he never really proposed, and someone else ends up proposing in that particular block height eventually. So yeah, these are the two kinds of slashings. I think that was quite a mouthful, so any questions? No?
On the inclusion preconf, cannot it happen that I do a preconfirmation for a block that's, I don't know, like, my turn is 5 blocks away, but someone includes it before? Like, and then the preconfer and the proposer wouldn't match. Right? Is that true?
Yeah, so in this case, we actually have discovered a few issues. So another variant, a more simple variant of your issue would be, I preconf, and I don't include it, but then for a long period, no one actually includes any block. So what happens is a long time passes, and the dispute period gets over. So even though there is no preconfirmation, there is a preconfirmation, but there is no associated block. Like the block ID has never really progressed on chain, and that's an issue. But you can't really prove the incorrectness of this. So we have a way of doing that, and so we might have to go back to, so let's say this is like the slots, okay? So whenever a preconfirmation is being made, we also include a lookahead pointer, which basically points to which slot in the lookahead am I preconfing for. So in this way, what we have to do is we have to make a connection between the preconfirmation and the proposed block via the lookahead. I think now that answers your question, because if we have that lookahead pointer, that basically states which lookahead slot have we made the preconfirmation for. And if it lands at a different time on the L1, we can make the inequality.
Okay, but is it possible that I pre-confirm something and someone includes it because they are a proposer before me? Or that can happen because they would be pre-confirmers for that slot before, so that I wouldn't be able to even include this as part of the pre-confirmations. I don't know if that makes sense.
I mean, not really, because because the proposer is once again this is advanced proposals. I mean, you just you just release it in the public mempool,
yeah.
And it might happen that the proposer does not include it, but then your slot will be coming in. So if you go back to this slide that Ahmad presented, in this case, when your slot comes in, you clear all those pending transactions that have never been included because the proposer didn't want to include, but your slot has now arrived. So you pick those transactions, and you force include it via the inclusion list through the PBS pipeline. Yeah,
the other answer to this question is that the previous preconfer cannot, the previous slot, if you're talking about, if this slot is for preconfer 2 to preconf at, the preconf 1 cannot then go and push transactions there. Every slot has an assigned preconfer, and only a specific preconfer can push transactions or batches in those slots. So the contract will just ignore any batches that arrive from preconfers that are not assigned to these specific slots.
Okay, perfect.
Any more questions? No? I think we can touch upon the future work now. Yeah.
All right. So first, we start with soft blocks. So currently, what we do when we advance the head is that we push a whole full block to Taiko Geth. And in this way, what ends up happening is that it goes and lands in the canonical chain, and this is normal. And this is why those transactions are then removed from the mempool. So when you propose the next block, they don't get included twice. So that's one thing. The problem with this approach is that when we are proposing these blocks at the end on L1, we need to propose multiple blocks. So for example, if I pre-confirm in every L1 slot around 4 batches, then that means that I have to make 4 proposals on L1. And this is costly. Proposers and verification of these blocks is costly. For a block proposal, it costs around 200,000 gas, Anshu, right? Yeah, give or take.
Yeah.
And around 400 for verifying the ZK proof for a single block, give or take as well. Could be a bit more than 400, more closer to 500. So every block that we end up proposing is adding a lot of cost for proposal and verification. So what did we end up with is a solution where when you preconf, you're going to add the batch to Taiko Gesh, push it, and then when you push another batch, what ends up happening is that it gets added to the block instead of being, so it gets appended in the block. So what happens is that a new block is formed with the previous transactions that are in the block, and the new transaction batch, and the previous block gets reorged out, and then we include the new block. And this keeps happening until the preconf node sends end of preconfirmation, and then this block becomes a standard block and gets pushed to L1 as a whole single proposal. And this gives us the cost saving that we're looking for, but it's still not finalized. It's something that we're going to hopefully work on the next couple of months. Another thing, like our friend here asked about before, is the slot time for the L2. So currently, we have a constant 3-second block time. And what we're looking for to accomplishing is 1 second block time. And it's not that this is not possible currently. It just hasn't been tried yet. And we're not sure what limitations we're going to hit with the P2P, etc. Yeah. And then in the last one, I think you will talk about it.
Yeah. So when I was talking about the preconfirmation service manager contract, I said we are trying to make it like a middleware so that as and when we want to change the restaking service or the staking service, we can just swap it out and use a new one. And in regards to that, the community is planning to launch a universal preconfirmation registry. So chances are there will be many more based rollups down the line, not just Taiko. And when you have so many based rollups, it could be the case that one proposer wants to propose or preconf for multiple based rollups, but it doesn't really want to register continuously because that will cost him a lot of gas. And also, it won't be that credibly neutral because might be the case that every rollup starts up its own staking service. And that's not reasonable for the proposer, and that's a waste of ETH, not a good use of collateral. So in this case, there will be a universal preconfirmation registry where any proposer who wants to become a preconfer can go in, register the BLS mapping instead of being in the protocol-owned registry. It will be here in the universal preconfirmation registry. Along with that, so the slashing condition opt-in, this is a very important aspect. So the rollup protocol, like whether whoever makes another based rollup, might want to have their own set of conditions based on which they want to slash. So maybe they don't want to slash inclusion preconfs. They want to just slash execution preconfs. So they can define their own slashing conditions and then only have those proposers who have opted into these slashing conditions be preconfers for their rollup. So yeah, this is still an ongoing discussion in the community, and eventually we will be speccing it all out and releasing it, but yeah, it's going to be a while. Well, that's it. Thank you so much. Okay, there's a question here. How do you see this integrating into existing KYC systems, or rather the path to scale and adoption on the side of users and institutions?
I'm not sure that's a question for the session.
Yeah.
Yeah. All right, so any questions? Final.
How do I evaluate the security of a preconf? Say I send you $10, I probably have it here. If I send you $10 million, how do I know if they say way that is fine or not?
Right. So what you're asking about is the fair exchange problem. And this is something that our research team has been looking into for quite some time now. As of now, we don't have a solution for the fair exchange problem. And I think most of the existing or proposed solutions depend on a reputation system as of now, where if the preconfer or the gateway providing the preconfirmation is acting maliciously, this would affect the reputation in a bad way, and they would potentially be cut out of preconfing for the specific protocol they're working on, and this would potentially lead them for losses. So the reputation-based system is being proposed for now, but we are working on a non-reputation-based system where there is some oversight over how the preconfers are acting and if they are actually preconfing in the correct time, providing preconfirmations in a timely manner without delaying the preconfirmations by coming from the users, or reordering transactions with this delay to just generate more MEV or profit for themselves.
There's another question here. What kind of slashing conditions do you see? Is it a penalty or more tougher? So I think right now our slashing condition is very straightforward. We just slash the entire stake, which is not ideal, and it's definitely not going to be this eventually. I think there is one proposal by the research team, and that's we have, let's say, slashable tickets. So for every preconfirmation that you provide and every validator that you register, you have a fixed amount of stake. So for preconfirmations, let's say you are staking 1 ETH for every preconfirmation that you provide. And once the preconfirmation is settled, you can basically reuse those tickets. But if you mess up that preconfirmation, only that 1 ETH amount will be slashed and not your entire stake. So this is open for discussion. And once again, I think this will be a part of the community-led discussion of how seriously we want to slash a malicious preconfer.
Sorry. How do you think distributed validator technology fits into your preconfirmation design? Do you think it could make it much more secure? Or have you guys looked into that?
So in DVT, I'm not entirely sure about the block proposal and how it works exactly. So I know that for the attestation, multiple, like 3 out of 4 nodes, they need to sign basically to get a proper signature, a BLS signature. And I think it's kind of the same for the proposal, but I'm not sure how they choose which one of the nodes is the one who's responsible for forming the block. So honestly, no, we have not looked into how DVT would interact with this protocol at this moment. Because also DVT does not form a significant share in the market of proposers as of now. So it might not make sense for us to look into it in a serious manner. But potentially, if it becomes more popular, then yeah, this would make sense.
Do you have any website for network metrics? How many validators are subscribed to this kind of stuff? Are you measuring live or?
I mean, this is not yet on mainnet because firstly, we don't even have the precompiles yet. We need to have the Pectra upgrade. So it's running on testnet, on Helder testnet. Have you heard of Helder testnet? It's a devnet, which was released during ETHCC. So Taiko already has not the final version, but one of the intermediate versions running on Helder, providing preconfirmations. But once again, that's a devnet, so it's only the validators that Taiko is running. But yeah, this was tested using 300 validators, and it worked great. Yeah.
Okay. Thank you.
How do you decide how much to pay for the preconfers? Because there might be multiple based rollups, and they might be compete for one preconfer.
If you can speak to the mic, because I didn't hear half of what you said.
Yeah. How do you decide how much you pay for the preconfers to propose the rollup blocks, because there might be multiple base rollups and for the slot, and they might be compete for the same preconfers.
So for the payment, we have lifted up for the market. And because we decided that the priority fee will be used, then basically the preconfers will just not preconfirm transactions that are not profitable. So any transactions that do not have a high priority fee that is paying the preconfer enough will just not be included, because the preconfer has the incentive to include as many transactions as it can in the block to potentially extract as much value as possible from the blob that it's pushing, because the blob has quite a lot of space. So the more data I can fit in a blob, which is basically now free, one way to get a blob as of now, the more I can make money. So we lift the pricing to the market to decide. There are some research that is going on in the space by Connor and Lynn from Nethermind, and there's another guy, I think, called Finn.
Finn,
yeah. I don't know their full name, so I apologize for that, about the economics of preconfirmations and the pricing for preconfs, etc. And this work, there is a lot of talks that Connor, Finn, and Lynn has been talking about preconfirmation. I advise you to go check the recordings for these talks by these people. They touch exactly on what you asked about.
Thank you.
How do you think layer 1 entity affects the liveness of the protocol? So, do you think it improves it? Is there a reason for concern?
Personally, like MAV or not MAV, the protocol works with local built blocks and also works with forced inclusion through PBS pipeline. The only problem here that I see is that if relayers and builders decided that they're not going to adopt the constraint API that we talked about, because it basically reduces their income because preconfirmations are not profitable enough compared to what they can include other than these transactions, then we would have a problem. But as of now, and as we heard from our partners, is that there's a lot of talk, and the relayers and builders are agreeing to add the constraint API to the EPBS pipeline, so they would be potentially including preconfirmations.
To add to this, I think we also have plans for L2 MEV extraction. So when that is added to this, I think the dynamic changes a bit.
Yeah, so basically, since we have like currently 3-second and potentially 1-second block times for the L2, in this 1 second, you can, the preconfer still at will can reorder these transactions. But we would not expect every preconfer, which is basically just an L1 validator, to have the sophistication needed in the software and in the hardware to be able to support such ordering in 1 second. And I think what's going to happen is that there will be a PBS pipeline for L2 blocks if this protocol gets adoption that tries to extract MEV from these L2 blocks in this 1 second slot.
Sorry, last question. What are the latency figures that you guys have regarding like the block transmission from the preconfers?
We don't have that yet because as of now we have only devnets, and devnets are basically just kurtosis set up instances that are running on local machines. I mean, we have Helder, but Helder deployed a hybrid solution between gateway preconfs and our solution. So our smart contracts, but gateway software, basically. And as of now, that's deployed in Helder?
Yeah.
Okay, yeah. So that's what deployed in Helder right now. So it's not the same, and we don't have that distribution of sidecars running so we can calculate this latency. We can do some simulations potentially, but yeah, reality always is different than simulations.
Do we have more questions?
All right.
That's a
Thank
wrap.
you, everyone, for attending.